Oh yeah, this is basically me, if you haven't recognized. So thank you for the invitation into this conference. It's my first time, but I hope you will enjoy my talk. So yeah, my name is Andrey. I'm CTO of Qdrant, and I am working in information retrieval for quite some time already. Started basically as a backend engineer in like a web scale search, then later switched to more into machine learning, and now I'm working as a backend engineer again, basically. And in our company, we are building this vector similarity search engine, also known as a vector database, but I actually prefer the vector search. It's a bit more accurate term for us. We are open source, so please feel free to give us a star on GitHub. Full commercial license written in Rust, so probably this is a last marketing slide you will see from me today. But in Qdrant, we are heavily focused on engineering and low-level stuff. We are basically a database company. I don't even call ourselves an AI company, even though we are in this kind of fundamental block of AI stack. But sometimes we do research in those cases where it's some kind of a low-hanging fruit. And today I'm going to talk about this kind of internal pet project research of ours, which I think turned out to be an interesting story. So I was promised that it will be a technical audience here, so I expect that you already know what vector embeddings are. If you do not know what it is, please feel free to ask me later on the backstage. I'm happy to talk with you about it. But in general, the idea is that there are two different kinds of embeddings which exist inside this vector space community. The first one is traditional dense embeddings. It's something you are probably familiar with. Please raise your hand if you are familiar with dense embeddings. Oh yeah, good. Then I can skip next 10 slides. And the second option is so-called sparse embeddings, and this will be our focus today. So we are going to talk mainly about sparse embeddings. To give you some intuition what it looks like, I have this slide here. It is not strictly universal representation of sparse embeddings. There are different models which can do it in a bit different way, but the idea is the following. You have a sentence, your document, your query, you tokenize it, then convert words into IDs, and some model or algorithm assigns weights to those IDs, and as a result you get this nice sparse vector. As you can see, only a few dimensions of this vector actually have values, and everything else is considered to be zero. That's why it's called sparse. I guess the main idea why you want to use sparse vectors versus dense vectors is because you want to have some kind of guarantee about exact match of the words inside your query versus your document, which regular dense embeddings cannot guarantee you. And if you take a look at this evolution tree of different models, you can notice the two distinct branches. The first branch on top is associated with dense models. It started as a word-to-vec embeddings, then it's sentence transformers, then it's contextualized inverted lists, and then the latest one is this Colbert models. Each step associated with some feature, some key component which changed. And on the bottom side, it's actually about sparse embedding. So we start with a bag of words, or BM25. It's something also you probably saw in regular text engines whenever you just use a keyword match that's called BM25. And those models, they are also going through the evolution. They added more intelligence to sparse vectors. They extended representation in different ways. And it might be overwhelming at first. So when you start researching this field, probably the first thing you will find the article with this table inside it. And this table is actually really hard to read, not only because it's small blurry numbers, but also because it's kind of lying to you. So the idea here is there are two different types of sparse models. First one is model without expansion. That means that each token in the original document is strictly associated with another token, another dimension in sparse vector. And models with expansion, they're actually a bit more complicated. They introduce new dimensions into the vector, even though some tokens might not exist in the original document. And I'm saying this table is lying because this last two columns in the first block, this split models, they actually do have token expansion. Is just implicit inside the model. That's why you might have expectation that they work better, even though they actually just hack it by introducing more data into the pipeline. But overall, what I want you to notice in this is that there is a baseline. The baseline for all evaluations of sparse models, it's a BM25. As you can see, the models which do not have expansion, that's fair models over here, they all perform worse than even a baseline. And it's kind of surprising because there are a lot of papers which were saying that, hey, our models is very good, please use our models. We spent so much time training them. But as a result, even though they used BM25 as a kind of hard negative examples during the training, they still lose performance if they are compared on like out of domain data. All of them practically except for those two split models over here, but we already discussed they are cheating and they are not actually without expansion. To simplify this diagram maybe a little bit, there is this research which says that only a few models are outperforming BM25 on out of context, out of domain datasets. And as you can see, some of the models are very far behind, and they are losing in almost all cases compared to the default baseline over here. And it's actually very sad. It's something we trying to fight in the industry, but there are not yet ready-made solutions which kind of satisfy all criteria. The wrong direction. So to reiterate over this evolution slide, what we can see is that it's not so great looking so far, right? Because some models just introduce too much overhead into pipeline. Some generate more data than needed. Others are just very slow, or at the same time they can not perform as good as you would expect in real life situation, where you have your own custom data sets and you cannot really afford special training for them. So to simplify it even further, what I want to say is that actually there are only two models which are used in practice in real life applications. So it's first, of course, it's BM25 because it's very easy. It does not really require any inference. It's practically as cheap as a text search. But it only provides this baseline accuracy you probably saw 20 years ago in any text search engine. And there is a split model, which does provide better accuracy, but at a very substantial cost. First of all, it's very expensive computationally, and it's also requires this token expansion, so you actually will store much more information in the database, much more dimensions in the sparse vector than traditional BM25 models. So we don't like this situation. That's why we started thinking maybe we can come up with something which is better. This is a small diagram which would demonstrate what we actually want to achieve. We want to be somewhere in between. We do not want to spend as much computational resources as Splat does, but at the same time we want to boost accuracy over the baseline. And the most important thing here, we want to do this in a way that we will not rely on the specific domain training. So we want this model to work practically in any live scenarios without fine-tuning, without any additional extra training, so out of the box. Basically the same way as dense model work, you just download them from Hugging Face and then work. And our goal is to achieve the same here in sparse vectors. So how we do it? Well, generally there are two ways how to beat BM25. The first way is to rank better, just come up with a better ranking function. And the second one is retrieve broader. It means that you include more tokens, you will retrieve documents which do not exactly have exact keyword match. And it seems like everybody is doing just this. So Splat is doing this, dense vectors are doing this, and we want to do a bit different. We want to actually rank better, and something we didn't see that often. So let's start and think about cases where BM25 actually cannot perform that well. First obvious case is distinguishing between different stems. By stems, I'm here mean like the lemmatization process where we kind of convert the words into normal form or some kind of original form. Here it's a very simple process. We just cut off the head of the word, how to say the suffix, and this process does help BM25 to search for more matches, but at the same time it loses information that was originally there, right? So you cannot say that all of these words actually have the same meaning. They are all kind of coming from the same root, but at the same time they have nuances which BM25 just cannot distinguish. It's just all converted into the same token, and you have to deal with it. And the second case where BM25 cannot really help us is distinguish between homonyms. So we like this example about the bet. It's like our go-to word if we want to check something. So there are two obvious meanings for this word. First is animal, and the second one is about like a baseball, the baseball bat. Can you come up with 5 more meanings for this word? No. Okay, that's a tricky question because it's actually not obvious, but there are many more different like cases and situations where this word actually used in different sense. We will talk about it a bit later. So those two cases is our like goal. What we want to achieve in our model is to basically solve this problem. And if we can do this, we can practically say that we achieved a better performance or better understanding of the text compared to our baseline. How do we do this? And here I have to say that we took an inspiration from the model called COIL. It's one of the models which I showed previously in this evolution slide. And the idea here is that instead of generating embeddings for the whole sentence, we do generate embeddings for each word, but during the search we only compare embeddings for those words where tokens are also matching. right? So this is a diagram from the paper. It might not be obvious, but the interesting part here is that when we compare, we only take into account the words with the same token. So we do not compare bank to river. We only compare bank to bank, right? And this is the whole idea of this article. But the original implementation does have a few problems. First of all, it generates quite a big embeddings. If I recall correctly, it was something like 64 dimensions per word. It means that it will have a huge overhead in the storage. And also it uses not exactly the words, but it uses this BB embedding tokens. So if you worked with transformer models, you probably know that it can split the word in pretty random places. So you cannot actually use it in applications where it's important to match words in different forms. And the main problem of this model is, of course, that it was trained with BM25 as a hard negative example, but in the slide you saw that it does not outperform BM25 in this out-of-domain context. So we will try to fix this. Yeah, so obvious steps what we can do to improve it. First of all, instead of generating embeddings per BPA token, we will use proper words plus stammer. So we will kind of import this from the traditional NLP pipelines, as you're probably already familiar with, as tokenizer, text analyzer, all of this stuff we just reuse. Second step, we use much smaller word embeddings. So that's small that they can actually be used inside the sparse vector. And instead of training end-to-end, instead of training this importance of the word, we will only train the semantic. I guess I have a slide further about it. Yeah, so this is basically how we see our model in this evolution step. We do reuse vectors from this COIL model, but also instead of using trained importance, we use the same approach BM25 use, basically statistical formula, which will give us understanding which token is important and which token is less important. So in worst case, our solution just falls back to original BM25 and it doesn't lose performance because of it. So before we go into model details, we need to check if our approach actually works and how we can do this. So what we did, we took 1,000 sentences, random sentences from Common Crawl with a specific word. In this case, it's a bet. We embedded the sentences with just regular sentence transformer and visualize how those embeddings looks like. So those are embeddings for the word bet. It's ironically looks like a bet as well, but it's not intentional. And you can see here that there are clearly two big clusters. One associated with baseball. I guess the baseball is the biggest one. And the second one here is associated with the animal context. Those two smaller things here, these are like also legit ways of how to use the word bet. They are just rarely used in real life, and I guess one of them is about Batman as well. So it's like a clear cluster of meanings here associated with DC Comics. So having this, we kind of understand now that this representation does have a meaningful signal. So we are quite sure that we can use it. The question is how. And this is basically our proposal here. So instead of using just a regular bag of words, we will generate a small vectors. Each vector is meaningful within the context of a single word, right? So there is an example here. So you see the different meanings of the stem inform is associated with different values of the vector. So if those meanings are similar, similar IDs inside this vector are activated, right? And same for the bet. If you have this, you can distinguish different meanings of the same word. It's important to mention here that you cannot compare different words in this context. So it's not like word2vec, where you could compare different words and do some fancy math on the vectors. In this case, it only works within the same token. And this small vector is a source of our similarity information, which we denote here as an M. So it's the only formula in my slide, so no worries. It's not going bigger than this. And the idea here is that we combine this score from the meaning with a score from importance. This TF-IDF is basically imported from the BM25 formula directly. We only include this additional component into the formula. So it's very, very easy, very intuitive for those who already worked with the text search. And the model itself is also very simple. First of all, we do not want to train big models on our own. We know that there are companies which are doing this much better than we do. But we do want to reuse this already trained models to our advantage. So what we do, we actually train only a small layer on top of the traditional sentence transformer. So this dense word embedding is coming from something like SBIRD, and it goes directly into our miniCOIL word model. It's, again, a very simple thing. It's just one linear layer with the activation, which gives us this basically dimensionality reduction from big embeddings into small embeddings. And once we train this model for each word, we can stack them together and make inference for the whole vocabulary. I guess the important part here is that we do inference in a way that we only activate those layers which are actually responsible for a specific word. So even though the model itself might be quite big and might be maybe 200 megabytes of parameters, the actual inference time is very small, and we don't have to keep this model in memory as well. We can just load directly this part of the model which is responsible for the tokens we're currently processing. And everything else can be just evicted from memory if needed. And yeah, of course, we reuse a big chunk of knowledge which is coming directly from sentence transformers, so we kind of rely on existing models, and those models are getting smarter and smarter. So as a consequence of it, our model is getting smarter and smarter as well, and we don't even have to do anything extra. Interesting part is how we actually make the use of those small embeddings. They are not directly can be used as a dense embeddings inside vector search because they cannot be compared to each other, but they can be used as a part of sparse vectors. And here is like a small diagram which shows how it's done. So basically we took original bag of words. We know IDs for the original tokens, and we just map those original tokens into our 4D vectors and store them sequentially inside this bag of words. So you can say in a sense it would be a 4D bag of words, but it's so small, like these 4D vectors are so small that it practically gives us no overhead for performance. It's still a sparse vector. We can still use the traditional inverted index to search through the space, and we can even quantize and compress it if we want to go even further. So we can have like 4 bytes per word in this scenario, which is very nice. And this is basically the same thing altogether. We have a dense encoder which converts this dense representation. We then pass this dense representation into our head layer. And this head layer converts a bag of word into 4D bag of word with a miniCOIL representation inside it. Again, important thing to notice here that we do have a dense inference as a part of process. And it's actually a good thing because now we can reuse these dense embeddings in our pipeline and build a hybrid search for free. We can use a combination of dense embeddings and sparse embeddings, but we only have to do the inference once. That makes the overhead of miniCOIL model is really tiny compared to SPLED or something else. A few words about how we trained it. So we do train this model per word, so it means that we actually need to train about 25,000 small models. We do not need any specific labeling for this because we do not train the model end-to-end. So we only need to distinguish between semantics, and we don't care about retrieval metrics at this point because retrieval component is taken care by the BM25 and TF-IDF component of our formula. So that makes our training process really self-supervised. We can use practically any corpus of documents to do this. And the process looks like this. We collect a lot of embeddings from different sentences which have a specific word. Then we build some form of distance metrics using some teacher model. I'm going to skip this part a little bit. It's going to be too technical, but yeah, if you are interested in details of training process, yeah, feel free to ask me afterwards. And having this distance metrics, we basically use a triplet loss to teach a smaller embedding representation to replicate this original distance metrics built with full-scale embeddings. So we practically do dimensionality reduction using the triplet loss. And fun facts about our training, it's, yeah, as I said, it's full self-supervised, no labels required, and it's actually done on a single CPU. And this is, yeah, this is correct, it's not GPU, it's CPU. It's only need to be done like 25,000 times, but it scales really well. You can train it on your laptop if you want. And yeah, the most important part here is the benchmarks, of course. So we tested miniCOIL on the standard beer dataset. That's actually a full set of different datasets. You can see that, yeah, there is an improvement, definitely. It's not maybe as great as some articles reported, but keep in mind that this is out of domain. So this improvement in performance comes practically for free. You don't need to train anything. You do not need to think about if your model is correct or not. And in worst case, what you get is this model is just falls back to default BM25 precision. And compared to all other models, if you recall from the first table I showed, the drop in accuracy in those models was much more significant. And in our case, you can even use it for language it never learned. And what you get is basically the same as BM25. You will not have a penalty for this. You can try it yourself, of course. We included miniCOIL v1 into our inference library. It's called FastEmbed. It's open source, so you can go and download it. Please share your feedback if you try miniCOIL on your project. We are very curious how it goes for you. But that's how it works. It's basically 4 lines of code. You don't need anything else on top of this. And yeah, that's, I guess, all. If you want a full version of this article, please follow the link. And yeah, I'm happy to answer any questions.
Yeah, so thank you very much. Very interesting. And I think we have time for a few questions. Do we have some? Yeah. I will go around and pass the microphone.
Thanks for the nice presentation. You already mentioned that the computational effort we have to invest is basically similar to what we would need to do for hybrid search. So do you have metrics how miniCOIL compares against standard hybrid search?
So we compared it against the sparse component of vector search. We didn't compare it against the whole thing because now this variety of different options is just huge. But yeah, you are right that it actually depends on which dense encoder you use. If you use really advanced dense encoder, you will probably get less difference. If you use smaller dense encoder, then you will get bigger difference here. I guess the important part I forgot to mention is that, like, what would be your decision when to try miniCOIL versus just stick to default pipeline, I guess. And the answer here is if you see that your search gives a wrong ranking for your request, so it does include all the terms, but those terms probably not in the best order, then you can try it. If you find that your queries usually just do not return any result, then miniCOIL is not your choice. Then you probably stick better to dense embeddings.
Do we have more questions? Yeah.
Hi, thank you for the presentation first. My question would be, since you are comparing words, is your model language specific or is it multilingual since you are using some dense embedding in the beginning?
Yeah, great question. So our model is as language agnostic as the original dense embedding. So if you use something like multilingual transformer, you can train miniCOIL to be multilingual as well. If the original language, if the original transformer is strictly English, then miniCOIL as a result will also be strictly English. It will fall back into just PM25 for all other languages, so it's safe to use it on, you know, multilingual dataset where majority is English and some portion is other languages. You will not lose the accuracy in this case, but if you want to boost your accuracy, you would need to train it for different languages.